if we're only looking at the projectile portion of the problem, so this is the second FRQ. Oh no, it's the first FRQ. So, but this is part C. We know that when the object leaves the ramp, it's leaving at an angle of 25 degrees and has a velocity of about 7.56 meters per second. So, here, let me throw this up on the screen. Yeah, no, give me a second. Is there anybody who wants to code? All right. So, this is 7.56 meters per second, and the angle is 25 degrees. So I'm under the impression you guys are all good with that. I don't have to review that. The projectile problem has a vertical side and a horizontal side. And our delta y is going to be -3 because we're leaving at the top of that ramp. Our initial y velocity is going to be that 7.56 sine 25. And our acceleration, -10 meters per second squared, you define t. This is Pythagorean theorem. I'm sorry, not Pythagorean. This is quadratic formula. That's it. But from what I watched with a lot of folks, you're just unwilling to take the time. And I know that sounds cruel, but I don't know what you expect I'm going to do different than what you're doing. 7.56 sine 25. What is it? 3 point what? Or maybe I'm the only one doing it. What's that? So your only choice, if you're going to solve it this way, is to get your A, B, and C and plug it in. Now, you don't have to do it this way. You guys are smart people. You can treat this as two parts and find out the time it takes to get to the highest point, and then find the time it takes to go from the highest point to the ground. That would alleviate you from having to do a quadratic, which means you would use you would say the initial velocity is 3.17, the final velocity is 0, the acceleration is -10. This would tell you how long it takes to get the highest point. You would have to find out how high that point is. And then you would do another problem where the initial velocity is 0, the acceleration is -10, and whatever this is, plus 3 meters, would be the delta y, and you'd find out how long it takes to reach the ground. You can do this. If you don't want to do the quadratic formula, this will do it, but you are not getting around the fact that you need the time that it's in the air. There's just no other way to do the problem. And I watched as everybody tried to squeeze this into their calculator terribly. Just be big. It is -3.17 plus or minus the square root of 3.17 squared minus 4 times -5 times 3. Just write it out, then divide the whole thing by 2 times -5. There's no way around it. And when you look at it clearly, you can see that you don't need this answer. You need the -1. Because you're going to be subtracting on the top to give you a negative number, so you can have a negative number in the denominator and get your positive answer. But there is only one answer to this. Although when I walked around the room, I saw a lot of different versions of this one answer. It's 1.16 or 1.1. There's a different number if you use 9.8. But this is what I have to do. Now, this is why I don't want to do it. I don't want to do all this minutia. This goes into your calculator. If you didn't get the right number for the time, then take more steps. Figure out 4 times 5 times 3. That's 60. Put 60 in there. Then figure out 3.17 squared. What is 3.17 squared? 10.05. Add together 60 plus 10.05. Find the square root of 70.05. It's got to be 8 point something. I mean, just doing these pieces in your head, it's not so much. 3 minus 8 is negative 11 divided by negative 10. That's 1.1. But you guys, you trust your calculators just too much, I'm afraid. And maybe I'm wrong. Maybe you got it wrong for a different reason. But this is how it's done. All right? So once you get your 1.16 or whatever your seconds are, your Vx is still going to be 7.56 cosine 25. Got your time, find your range. It's 8 meters for sure. 7.56 plus times a little bit more than 1. That's going to come out to be about 8. All right. I'd say that was fun, but it's not fun at all. So if we consider that at the top of the ramp, it's still sliding. It has 1/2 mv squared. And at the top of the ramp, it's still rolling 1/2 I omega squared. And now it is 3 meters above the ground. We could compare these two energy states, and this is what you did to figure out the velocity, correct? You probably linked these together and found that this was 7/10 mv squared. And this, of course, will still be 7/10 mv final squared plus mg times 3. And this is how you figured out the velocity. We good? Now, here's the problem. There's no friction anymore, which means there's nothing to cause the rotational speed to change. Are you hearing that part? There's nothing to cause the rotational speed to change. So whatever the rotational speed was when it hit the bottom of the ramp, it's still the same rotational speed at the top, so this no longer applies because V does not equal omega times R. This applies still. But this value, the rotational speed, never changed, so it's the same over here. I still have to give up this much energy, 750 joules, has to be given to the gravity Earth system, or to the Earth ball system. But I now can't pull that 750 joules from the rotational energy. I can only pull it from the translational energy. There's less of that available, because now it's only 1250. So that's why. Mathematically, that's why. But also, if this were a block that was just shot towards a ramp, we wouldn't have thought anything of talking about its speed at the top of the ramp. If we said there was no friction, it would just slid up there. But the fact that it's rolling, if there's friction, the object that's rolling gains traction. The fact that it's spinning allows it to dig in and pull itself up the ramp because of its spinning. With it sliding, the wheels just keep spinning. There's nothing for them to grab onto, to apply a force to get it to go up the ramp. So, yeah, it's going to be going slower, no doubt. Are there more questions about this that I can try and answer and try and relate? Second FRQ. We ready to talk about that one? I think the second FRQ is tough. It's tough for a lot of reasons. But I think a lot of students have more difficulty with this than they probably should. I think they read it wrong. This came out in 2012, and the response on it was not good. Students did not do particularly well on it. So this is why I don't give it as a test, because I am familiar with how students do, and I get nervous of what I would expect if I ask them to do this on a test. So there's a region where the ring encounters friction. So before that, it's sliding, and it has a velocity of v naught. At t equals 0, it encounters this place where there's suddenly a frictional force applied to the ring. And it's at this instant that t equals 0, and we begin our problem. They tell us that the object will traverse a distance L before it is rolling. That when we make it to here, it's now rolling. And it's rolling without slipping after it makes it to distance L. Now, it should not be lost on you that the object's going to be going slower. Right? It's going to have to. But let's explore this a little bit. And here's where, if you have your math appendix open, have it open to the part where we talked about differential equations back in October and November. Now, if you didn't take notes like that, or you can't find that in your notes, I would strongly encourage you this semester, create a section of your notes that's just about differential equations. Because the moment we are done with this angular momentum stuff, we're going to do all the math we couldn't do first semester. That's before we go into gravity. We're going to do differential equations, and we're going to do them for some challenging questions, like questions involving air resistance and drag and terminal velocity. Those are some more complicated mathematics. You're going to want to have a place in your notes where the basics are sitting there in front of you. Also, this problem told you where to begin. They didn't keep it quiet. So this is a parallel discussion. I'm going to explain this FRQ, but at the same time, there's some math you need to write down. So how you take your notes, of course, it's always up to you. But when I start switching over and talking about math and differential equations, you should probably write some things down and just have those available. I'm not trying to tell you this on your next test. I'm not. I'm saying that we need to be able to do this. This whole FRQ really had a lot of it in it. And if you couldn't do part A, you probably felt like you were kind of stuck. So let's talk about what they are telling us to do. We need to create a differential equation. It says it clearly. Starting from Newton's second law in either translational or rotational form, as appropriate, derive a differential equation that can be used to solve for the magnitude of the following. And it is the velocity that they want. Now, a differential equation is just an equation that contains a differential. There are two differentials that should be on your mind when this pops up, because they are the most common differentials that we have. Now, we have other differentials. These are not the only ones in our class. Like power is a differential. It's dw dt, but we really didn't talk about it very much. And we would never use this one to create a differential equation, or it'd be very unlikely. But those two differentials are very likely. And they are differentials. It tells us that the acceleration is the rate of change of velocity. That's a differential. And the velocity is the rate of change of position. That's a differential. So let's just keep those in the back of our minds. If you are asked to make a differential equation, there's only two real places to look. You need an equation with velocity in it. This will give you a differential for x. Or you need an equation with acceleration in it. This will give you an expression for v. Now, There's not many places where those exist. There's not many expressions that have v in them that you can use to create a differential equation. I think there's only like 2. There's not very many places for you to get an acceleration to create a differential. The number one most likely place that you will ever create a differential is Newton's second law. It is the number one most likely place. And all the things we've done so far, it's always been Newton's second law where we've created a differential. So them telling you to use Newton's second law, that was pretty nice of them. I don't think they had to. They said to start here. Now, I can immediately create a differential equation. The moment I substitute in dv dt for a, I have created a differential equation. That's what that is. I can't turn this in, but I've created a differential equation. The problem is that I'm not allowed to have sigma f. That's not one of the allowable variables. I'm going to have to do something with that, but that's it. The problem is done. The differential equation has been written. That's all they want is a differential. Now you have to get rid of net force. You probably have to come up with some stuff here. Like I would probably help you out and say that this is probably talking about the net force in the x direction. So to me, that means I replace net force with the only force in the x direction, friction. Of course, friction's not allowed to be in my equation either, but that's okay. I know about the net force in the y direction. That's got to be 0. So normal has to equal mg. I mean, I didn't draw a diagram, but is any of this a surprise? I'm doing this because it says friction. And friction equals mu n. This is kinetic friction, by the way. It's not static. This object is sliding. So it does not have a point that is in contact with the ground that's not moving. It's sliding across the ground, so it's kinetic friction. It's a constant. So I can sub and get minus mu mg equals m dv dt. I do see that there's an m on both sides. I am going to take care of that. And this is what I would finish with, and I would say this is a differential equation that could be used to solve for v as a function of t. That was it. Now, you do the same thing for torque. I'll give you a moment. Newton's second law for torque. That should give me just enough time to pour a cup of coffee. Are we done yet? See a few of you still working. Good, good. I am noticing that the frictional force applies a positive torque about the radius of my ring. So my torque will be R times F. I notice that this torque is going to speed up the ring, so I'm making it positive. Unlike the frictional force slowing down the ring with net force. Although I can cancel out one of the R's, I probably also realize that I can write force as mu mg, cancel out one of the R's. And I can replace alpha with d omega dt. the angular version of the differential. I can cancel out an m, but that's it. We're kind of stuck there. This is as far as I can go. I mean, I could get the r on the other side. This is not necessary. It's a differential equation, even with the r on the same side as the differential. But in a few minutes, we're going to solve that differential, so it makes sense to get it by itself. But a differential equation is just an equation that has a differential somewhere in it. We're there. So that was it for part A. Ready to go for part B? I was going to drink out of this. That's probably a bad idea. Ready to go for part B? Are there more questions here? So part B okay? Before I go into part B, this is a process. What we're going to do now is not physics. It's a process. I'm going to highlight the things that I know AP graders want to see as a part of this process. But I'm also going to say, you could have cheated. Do you notice that this is a constant? Right? It's not changing, it's a constant. That as the object slows down, this number doesn't change. Well, because that's a constant, you could just use Galileo's motion equations. Just drop it in. I don't know if they'd allow it. They said derive. That doesn't feel like derive. I would bet in a test that's any newer than this one, and this one was 2012, they would say specifically to use integral calculus, that they wouldn't leave it to chance. But in the prior years, they would not say that, and people would just do this. And sometimes they'd be forced to give them credit. I don't want to take the cheap way out. I want to do what I think they will ask of you under these circumstances. This process is called splitting the differential, and we've talked about it before. I'm going to go through the set of steps required to split the differential. If you don't have these in your appendix someplace, you need them, because it will get harder. This is as easy as I can make it. So, if you understand where all this came from, the next couple of parts are not particularly hard, but they're not physics. Step one to split your differential is to, quite literally, multiply both sides by whatever the denominator of your differential is. So, I'm going to get dv equals minus mu g dt. Convention forces me to put the dv on the left side. It doesn't have to be there. It's the convention for me. Years of doing this, I always have the variable that I'm searching for on the left side of my equation. And we want an equation that had v in it. But that's the only reason I flipped it around. Does everybody understand? It serves no other purpose. Next, and this is probably the more important step, the step that here is meaningless, but in the future is everything. V and t are now suddenly very important variables. They're inside the derivative. And they're telling me on the left side that the left side has to be about v and the right side has to be about t. So my next step is to get and collect all of the v's and put them on the same side as dv. And collect all of the t's and put them on the same side as dt. Now, this goes for any derivative. It could be dw dx. I don't know, but you have to collect those variables. And this is something that's going to sound kind of weird right now, but trust me when I say it's not weird. You're only going to be able to use multiplication or division to do this, never adding or subtracting. Because there's going to be one in about 2 weeks, so you're going to look at it kind of weird. But the only way you can do this is by multiplication or division. Now, there is no v and no t here because it was a constant. So I've already done that step. The next step is to just draw in your integral symbols. And set your limits. So draw in your integral symbols and set your limit. I want to pause here because you guys who are in calculus, we do this different in my class than you do in calculus. So for you guys who aren't in calculus right now, just ignore this for a minute. In calculus, you would do this as an indefinite integral and get a single equation-wide constant, c, that you would then use your boundary conditions to solve for c. I am telling you, don't do that in this class. I'm telling you to do it my way, because AP Physics in every single grading guidance I've ever seen, they always want to see the limits on the integral. So please, do this my way as a definite integral, even though truthfully, these are indefinite integrals. I know it doesn't make any sense, but you need to trust me. Every single grading guidance shows it this way. So for the rest of you now, this is an all skate. We have to put in our limits. We have to tell it where it begins and where it ends. But here's the thing about this. This is different than a summation. What we did before was a summation. This is not. Although it effectively does the same thing, we have to link the left side and the right side together. So when you are putting in your limits, you are telling it where both sides start and where both sides end. For example, at time 0, the velocity was v0. I'm setting the bottom limit and I'm linking them together. They told me in the problem, way back when we first were starting, that at time 0, the object had a velocity of v0. I have to use that. Now, your upper boundary is an open boundary. We are looking for meaty hands. We are looking for some time in the future, so some t in the future. The object will be traveling at some v in the future. This is an open variable. It's really creating our function, and we're using functional variables for later. That's what I mean. For you guys, it feels like it's an indefinite integral, because it kind of is. We have no upper boundary. Now, I should just say, take the integral and be done. But I know that a few of you are still, struggling a little bit. So taking the integral is finding the antiderivative. So I'm going to find the antiderivative, but there is no variable here. So if there's no variable, we assume it's 1. But we don't just assume that it's 1. We assume it's whatever this variable is to the 0 power. And now we can apply our polynomial rule. Now, if there was a function there like sine of v, we would do a different rule. Whatever our function is that has to do with v is what we would do there. But because there's no function, we place v0 in there. It's the only reason we're placing a v, not v0, we place a v to the 0 power in there. This is so we can do our polynomial rule. Add 1 to the exponent and divide by the new exponent. And apply my limits. I'm going to do that on the other side, but I have a constant. I'm going to ignore the constant and just write it out front. And this is exactly the same. I have no variable there, so it's t to the 0 power, which is just going to be t evaluated from 0 to t. Now you just plug in your limits, which means put in the upper limit first and subtract the lower limit. So v minus v0. And t minus 0. Now you're done, really. We're supposed to have a function for v, though, so v equals v0 minus mu gt. All right. Now that's it for that side. But you have to do the other side. So can you do the other side on your own? I'm really saying that like do the other side on your own, please. All right, that's all the time I want to give to this. So we should be here now. Any questions about how we got here? So would anybody like to add anything or would like me to expound on this a little more? All right, so I'm going to move forward. I want to point out something that I hope you see here. This is getting smaller, right? It's starting at this number, and I'm taking something away from it every second. Does everybody see that? Eventually, if it goes on long enough, the object will stop. This one is starting at 0. At t equals 0, it's not rotating. And this number is getting bigger. So it's starting to spin faster and faster and faster and faster. Everybody agree with those two statements? Does it make consistent sense with what was pictured in this problem? That the object was sliding, hit a rough patch, and is now slowing down while its rotations are speeding up. Now, it's all in the language. And here's where I would say this was rough. You have to listen. And even every time I read it, it feels like it was just mean. Derive an expression for the time it takes the ring to travel the distance L. Boy, that sounds like it's about the distance L. If I were a student just seeing this for the first time, I would think that I'd have to somehow work L into my answer here. But that's not at all what it asked. It said, derive an expression for the time. It wants an expression for t. This will end with t equals something. Now, here's the trick. It wants to know when the object makes it a distance L. What is a distance L? What the hell are they referring to? Do you know what they're referring to? What happens at L?
The translational velocity and the rotational velocity are proportional.
What were you going to say in the back?
Oh, I was going to say it's just sliding rotating.
What were you going to say?
I was going to say it's when the velocity and it's rolling past the bank.
So these are all the same thing. But one of these is actually helpful for us right here. It is the moment it is rolling without slipping, which is when V equals omega R. At L, this has to be true. They want to know when this happens. Notice there's no t in that equation. But I have an expression for a number that's getting smaller. This number is getting smaller all the time. And I have an expression for this number. This number is getting bigger all the time. I want to find when those two things are the same. So plug them both in and solve for t. So remember, we want when this is going to happen. L was a placeholder to tell us where this happens. Now that's it. I cancel out the r's. And I'm going to add this to both sides. And I'm going to solve that for t. This is when that happens. And you can test it a little bit. If the thing was moving faster, do you realize it'll take longer for it to finally start rolling? That makes sense because it's in the numerator. If the surface was sticky, then that number would be bigger and it would take less time for it to start spinning. That makes sense too. Sticky surface is going to make it spin sooner. All those things make sense. Worse, the top is in meters per second. The bottom is in meters per second squared. It comes out to be seconds. And this 2, that's probably where the mr squared went. Right? We don't see the shape anywhere in this. I bet we'd have a different number there if it was shaped differently. Now, there's 2 more parts. That was the hard one. If you got over this one, the other parts are easier. The next one is derive an expression for the magnitude of the velocity. I know when it happens now. If I want to find out how fast it's going, plug it back in. I know when it's rolling. Let's see how fast it's going when it's rolling. So V equals V naught minus mu g times V naught over 2 mu g. The mu g's cancel out, and I get V naught over 2, so this must happen when we are at half the speed. I would have never predicted that. I bet that has to do with the fact that it's a ring. I bet. I think a solid sphere would probably do it sooner. It's easier to turn. And now, derive an expression for L. Now look, you could go back here and create a new differential equation. But I'm thinking delta x equals 1/2 a t squared plus v naught times t. I think that's the way to go.